This is section 18.4 on the cardiac muscle fibers or cardiac muscle cells. I'm not going to do a lot on this, but I do want you to know, in comparison to the skeletal muscle fibers or cells, cardiac muscle cells are striated, just like skeletal muscle, but instead of being elongated, they are short and branched. And they are interconnected by a structure called the intercalated disc. And instead of multiple nuclei, there's just one central nucleus in a cardiac muscle cell. So the intercalated disc are connecting junctions between cardiac cells. They contain desmosomes to hold the cardiac cells together in a strong attachment so that when the heart contracts, that they don't pull apart. And then also there are connections called gap junctions that allow ions to pass from cardiac cell to cardiac cell. And that allows for a coordinated contraction where all of the cardiac muscle cells are contracting as a coordinated unit. So this is looks like a light microscope image of cardiac muscle cells. You can see here the branching, you can see the intercalated disc, you can see the central nucleus. The gap junctions, which contain a channel for ions to pass, and the desmosomes are the strong attachments that keep the muscle cells from pulling apart when the heart contracts. Now, we're not going to focus a lot on the physiology of a cardiac muscle contraction, but it is important to know that some cardiac muscle cells are self-excitable. There are two kinds of myocytes or muscle cells. There are contractile cells, which are responsible for contraction, and then pacemaker cells, which spontaneously depolarize and initiate the depolarization of the entire heart. They are, because they're pacemaker cells, they don't need the nervous system stimulation. So they just spontaneously depolarize on their own. Now, the nervous system and the endocrine system can control the rate, the heart rate, whether it increases or decreases, whether the heart beats fast or slowly. But the pacemaker cells are going to spontaneously depolarize, on their own. They don't need nervous system stimulation. Now, as far as respiration, breaking down glucose and in the presence of oxygen in order to produce ATP, this does occur in the mitochondria. The heart does rely almost exclusively on aerobic respiration rather than anaerobic. So the heart cannot function without oxygen. And now we're going to move on to this is chapter 19. I'm so sorry. We're going to move on to chapter 18, slides B. So I just need to find them. I'm sorry. Okay, I tell you what we'll do. We will go to on our Moodle page. Here we go. Sorry about that. So section B starts with section 18.5. And now we're going to focus on the electrical events of the heart. We just learned that, there we go. We just learned that the pacemaker cells depolarize on their own. They don't need nervous system stimulation. And we call this system the intrinsic conduction system. And the sequence of excitation begins with the cardiac pacemaker cells in the SA node or sinoatrial node. And then that leads to an impulse traveling to the AV node or atrioventricular node, then the atrioventricular bundle, also known as the bundle of His, H-I-S, the right and left bundle branches, and the Purkinje fibers, which your textbook calls the subendocardial conducting network, or Purkinje fibers. The SA node is located in the right atrium. It's the pacemaker of the heart, and it depolarizes faster than the rest of the heart muscle. It generates impulses at about 75 beats per minute. And the impulse spreads across the atria and to the AV node. Then the AV node delays the impulse for about 0.1 seconds to allow the atria to contract and empty blood into the ventricle. The AV node has a slower rate of about 50 beats per minute in the absence of the SA node. So if there was something wrong with the SA node, your heart would still beat. It would just beat slower. The impulse then travels to the AV bundle or bundle of His, and that is located at the superior portion of the interventricular septum in the upper portion. And it's the only electrical connection between the atria and the ventricles. The impulse then travels to the right and left bundle branches, which are going to carry the impulse to the Purkinje fibers, which carry the impulse through the walls of the ventricles. And remember that the Purkinje fibers are also known as the subendocardial conducting network. There is a good video link, and this is slide number 11. And then this shows you the pathway from the SA node to the AV node to the bundle of His, the bundle branches, and then the Purkinje fibers or subendocardial conducting network. Now, when there are problems or defects in the intrinsic conduction system, you may have arrhythmias, which are irregular heart rhythms. You may have fibrillation, which are rapid, irregular contractions. And during fibrillation, the heart cannot pump blood. The circulation ceases, and it can result in brain death if not treated. Treatment is by defibrillation, and which basically stops the heart and allows the heart to resume normal depolarizations. And that is used, you can use those AED boxes that are located in, school buildings, government buildings, hospitals. Now, a defective SA node may cause an ectopic focus, which is an abnormal pacemaker that takes over pacing. If the AV node takes over, it's going to slow the beats per minute. Sometimes you have a condition called extrasystole, which is premature contraction, and that is the ectopic focus of a small region of the heart that triggers an impulse before the SA node, causing a delay in the next impulse. And basically, in this extrasystole, the heart has a longer time to fill, so the next contraction is felt as a thud, as a larger volume of blood is being pushed out. This can come from excessive caffeine or nicotine. I'm just sitting here thinking, I've never really been a smoker, except, just occasionally as a younger person, but nicotine, I can't remember really. It's been such a long time, but I've definitely had excessive caffeine, and I can kind of, I think I kind of understand what that feels like, that thud that you feel sometimes if you've had too much caffeine. It just kind of comes and goes. Don't try it, please, you guys. Do not try a lot of caffeine to see if you feel that thud. But maybe you're not like my children. But mine would hear that, and at least one of them would hear that and then try it, you know. So to reach the ventricles, the impulse must pass through the AV node. So sometimes if the AV node is defective, that may cause a heart block. And few impulses would cause a partial block, but no impulses would cause a total block. And in that case, the ventricles will beat at their own rate, and that rate is too slow. The person would die. So the treatment is with an artificial pacemaker. Now, even though the autonomic nervous system does not cause the heart to beat, it does not stimulate the heart to beat. You know, the heart has its own intrinsic conduction system. The medulla oblongata does have two cardio centers, cardio acceleratory center and the cardio inhibitory center. The inhibitory center is connected with the parasympathetic nervous system and uses the vagus nerve to decrease the heart rate. The acceleratory center increases the heart rate in different ways. Okay, an EKG or ECG is an electrocardiogram, which is a recording of the electrical activity of the heart, and it kind of goes along with us learning about the intrinsic conduction system. So the most typical amount of leads for doing an ECG is 12 electrodes. Now, the features of an ECG tracing are the P wave, the QRS complex, and the T wave. And then we look at the PR interval, the ST segment, and the QT interval to determine heart function. So the P wave indicates depolarization of the SA node, and that indicates that just a split second later, the atria are going to contract. So it is prior to contraction of the atria. If you're watching an EKG, the waves as you're also listening to someone's heartbeat, or as you're watching someone's heartbeat, if you were able to do that, you would actually see the P wave peak, and then you would see the atria contract. And then you would see the big QRS complex, which is that large pointed peak in the EKG. And then you would see the ventricles contract. And during that time, the atria relax, they repolarize, so then they relax, but you wouldn't really see that because the ventricles will be contracting at the same time. So then you have the T wave, which represents the ventricles repolarizing. The PR interval is the beginning of atrial excitation to the beginning of ventricular excitation. And then the ST segment is the entire ventricular myocardium is depolarized. And during the QT interval, that represents the beginning of the ventricular depolarization through ventricular repolarization. Here's a man who's connected up to the electrodes, and they are running an EKG on him. And then here are the peaks, the P wave, the QRS, and the T. And then this shows you what's happening in the heart at each point. The P wave is representing that the atria are about to contract. The QRS is representing that the ventricles are about to contract. And the T wave is representing that the ventricles are about to relax. Problems you can detect: if you have an enlarged R wave, that may indicate enlarged ventricles. If you have an elevated or depressed ST segment, that can be cardiac ischemia. And then if you have a prolonged QT interval, that can reveal a repolarization abnormality that increases the risk of ventricular arrhythmias. This is showing you a normal EKG rhythm compared to a junctional rhythm where the SA node is non-functional. And this is showing you a second-degree heart block. The AV node fails to conduct some SA node impulses. As a result, there are more P waves than QRS waves. There's 2 P waves for each QRS wave. In this one, and this is ventricular fibrillation, which is, I mean, it's just, you can always tell that one because it's just so erratic. We will start with section 18.6 in the next recording.